As per the instructions, I prepared the talk for 2.5 hours. So, due to the insufficient time, I will try to cut it down to 2 hours. So, is it visible? Are the slides visible? And am I audible? Thank you. How many of you are from mechanical department? Please raise your hands. Okay. And rest are from which departments? Okay. Which motivates you to attend this session? Is it forced or motivated? Okay. The complete session is divided into 3 parts. In the first part, I will go through briefly about the additive manufacturing. Why additive manufacturing? When do we use additive manufacturing? Why not conventional manufacturing process? And then in the second part, I will go through briefly about a few important metal additive manufacturing processes. In the third part, I'll give a case study on the design to manufacturing of a creative plant using hybrid machine learning additive manufacturing techniques. So what is additive manufacturing? What is additive manufacturing? You have been hearing about this term, right? Any students? Yes, speak out. What is additive manufacturing? You're final year students, right? Okay. So, as per ISO ASTM 52900, additive manufacturing can be defined as the process of joining materials to make parts from 3D CAD model layer upon layer. So it starts with a CAD model, you divide that into slices, and for each slice we try to make the path programming. As per the given information, the machine tries to deposit the material layer upon layer to make a 3D component. In simple terms, this is the definition of additive manufacturing. So let's try to understand the definition of this additive manufacturing using this video. So let us say I want to manufacture this complex component by using additive manufacturing. So this is the schematic representation and the corresponding video of the procedure. It starts with a CAD model. So this is the digital replica of a CAD model corresponding to this component. And then we try to slice this CAD model or the STL file corresponding CAD model. And for each slice, we try to generate the path programming. And this path programming for each slice, or the coordinates information of each slice, will be communicated to the machine, additive manufacturing machine. So here, the machine, the animation you are seeing here is one of the AM variant called as the powder bed fusion process, where we have a bed, deposition bed, and over the deposition bed, we try to spread a thin layer of the powder. And then, as per the given slice information, laser tries to selectively melt the spread powder Okay, and once the slice information is as per the slice information, once the selective region of the powder is been melted, the bed goes down to a distance equal to the thickness of the slice, and then again new layer spreads. Again the laser tries to melt the powder, newly spread powder selectively as per the slice information, and this continues layer upon layer to make the 3D component. So the first layer, as per the first layer information, the first slice information, the laser selectively melts the powder. Once it is been done, the bed goes down and new layer spreads, and again the laser traces the material as per the slice information to build the 3D component layer upon layer. In brief, this is the working principle of an additive manufacturing process. So these are few of the advantages of the additive manufacturing over the conventional manufacturing. The first one is the rapid product development process. In any product development cycle, first of all, you need to make the design. After making the design, you need to make the prototype. You need to realize your idea. Once the prototype has been made, you need to take the feedback from the associated customers which uses the technology or product. Once you get the feedback, as per the given feedback, we try to remodify the design. Again, you manufacture the prototype until you get, this cycle continues until the customer gets satisfied. So now, during this product development cycle, if you use the conventional manufacturing process to make the prototype, it tries to increase the product development cycle. In the sense, let us say if I want to make a product, if I go with the injection molding, I need to make the tools, dies, and this dies will take lot of time to manufacture. Okay, and now with each design, if you manufacture the dies, fresh dies separately and continuously, it tries to increase the overall product development cycle. Instead, here in case of additive manufacturing, we try to rapidly build the prototype from the given design. And if any modifications are there, immediately you try to implement those modifications in the CAD model and print the corresponding component. So this tries to decrease the overall production cycle by rapidly producing the prototypes. And high degree of customization. So if you have the customized products like the human implants or the prosthetics, okay, so or any the components related to the high value products, for example satellites, there we don't go for the mass production. Each component is customized as per the requirement. So for each customized product, you should not go with the making the conventional the tools for the conventional manufacturing process. So here, the high degree of customization refers to the customized products can be readily printed by using the additive manufacturing. This is one another advantage with the additive manufacturing. Next one is complex design. So here, the additive manufacturing gives you the design freedom. That means, whatever the complexity of the component, you don't need any specialized tooling. The same machine can be used for 3D printing the component. Again, it depends upon the type of the material and type of the size of the component and the complexity of the material. We try to choose the various variants of the additive manufacturing. Overall, additive manufacturing will give you the design freedom and the high level of automation. That means once you make the model and once you rectify your STL file for errors, and then once you slice it, before slicing, once you optimize your orientation process parameters, then once you slice it and give that information, slice information to the additive manufacturing system, your job is done. It is a part of the machine to complete the component. There is no need for you to interfere in between. So this a high level of automation is possible with the additive manufacturing. So if you see the articles or textbooks, you will come across multiple synonyms for the additive manufacturing. For example, the rapid prototyping, rapid manufacturing, 3D printing, additive fabrication. So all these terms, these are the synonyms for the additive manufacturing. So let's try to understand the importance of this additive manufacturing, in the words of the former president, US president.
Is making America a magnet for new jobs in manufacturing. After shedding jobs for more than 10 years, our manufacturers have added about 500,000 jobs over the past 3.
Is it audible?
Caterpillar is bringing jobs back from Japan. Ford is bringing jobs back from Mexico. And this year, Apple will start making Macs in America again. There are things we can do right now to accelerate this trend. Last year, we created our first Manufacturing Innovation Institute in Youngstown, Ohio. A once shuttered warehouse is now a state-of-the-art lab where new workers are mastering the 3D printing that has the potential to revolutionize the way we make almost everything. There's no reason that this can't happen in other towns. So tonight, I'm announcing the launch of 3 more of these manufacturing hubs, where businesses will partner with the Department of Defense and Energy to turn regions left behind by globalization into global centers of high-tech jobs. And I ask this Congress to help create a network of 15 of these hubs and guarantee that the next revolution in manufacturing is made right here in America. We can get that done.
So this is very popular address by the former president of US. So, and followed by, he realized whatever the words they had given, he realized those words with huge funding in establishing the additive manufacturing centers across the US. Okay, and in 2000, this address was made in 2012, not 2012, or somewhere between 2012 and 15 something. So at the time itself, they realized the importance of the additive manufacturing, and they tried to consider it as the next revolution in the manufacturing sector. Okay. So, and they invested hugely from the time itself. That's why if you see any of the additive manufacturing machines, most of the machines are from US and Germany. They invested a lot in developing the machines, not the products. So, that's the importance of the vision. So now,
is making America a
so however,
is making America a magnet.
So, however, the reaction among the business leaders it was not unique. There is a varied reactions from the industry leaders. For example, the General Electric CEO views additive manufacturing as a game changer, and they would like to invest hugely in the area of additive manufacturing. In contrary, the Foxconn CEO stated 3D printing is a gimmick and has no commercial value. So, what is the reason for this different views on the additive manufacturing? Why such divergent opinions on additive manufacturing? Why? Because an industry leader, they need to think about a lot of variables if they want to invest or if they want to consider additive manufacturing as a best fit for their manufacturing industry. Why? Because there are a lot of variants under additive manufacturing. Starting from the binder jetting and then the powder bed fusion process, radiant energy deposition process, sheet lamination process, and even under powder bed fusion process, the laser-based powder bed fusion as well as electron beam-based powder bed fusion. In case of radiant energy deposition, you have the laser-based DED, electron beam-based DED, wire-based DED, powder-based DED, okay, the arc-based DED, plasma-based DED. Okay, there are a lot of variants, and each variant has its own significance as per the type of the material it can process, the size of the component it can manufacture, the complexity of the component it can handle. Okay, and the complexity of the component it can handle. So, So then, how do we decide, okay, which process to use, and for which application we need to choose which process, which one is economical, and most of the and additionally, most of the components can be manufactured by 3D printing. Does it mean that it is superior over the conventional process in all the cases? How do we decide when do we go for additive manufacturing? When do we go for the conventional manufacturing? Which one is economical? For which purpose? For which application? For which product size of the product material? Okay, so we need to have a clear information on this. Okay, one should be clear, and there should not be any confusion before deciding to invest on the additive manufacturing. So that's where most of the industry segment leaders, they have different views on additive manufacturing. Okay, so there was one of the work published. They come up with a reference system to address this problem, and this reference system has three axes. Corresponding axes are attached to an attribute. For example, volume is one attribute, and the complexity is another attribute, customization is another attribute. What is the volume? That is the production volume. That is the number of parts made in a given time frame, such as the lot size or the order volume. And the complexity is the number of features a part contains, and more complex feature is difficult to manufacture with the traditional manufacturing process. The third axis, the third attribute is the customization. That is the uniqueness of the part based upon the customer design. So all the products in the present industry or the present application sectors, okay, falls in any one of these regions within this volume, within this cube that is being designed using these three attributes. So let us say the region 1, that is the mass manufacturing. So what kind of products can fall within this region 1? Can you explain with respect to these three attributes? So does these products have are so much complex? Or those are customized components? Yes or no? Yes or no? Does the products, what are the products falling under region 1? Are these products customized? Are these products complex? Are we going to go for mass manufacturing of these products? See the volume, see the axis. So the region 1, what are the products fall within this region? So they are in high volume and low customization and low complexity. That means the products which are very simple and which we want to go with the mass manufacturing, there we can go with the conventional manufacturing process. The additive manufacturing process is not economical. And the region 2. So this is the region 2. You can see, right? So the products falling under within this region 2, they are in those products. No, you don't want to manufacture in high volume. Let us say it's a product I don't want to manufacture in high volume. Okay, but and also at the same time those products are not complex and those are not customized products. Then which one I need to choose? Additive manufacturing or the conventional manufacturing? Additive manufacturing, conventional manufacturing. How do we decide? So the region 2 describes the products with limited complexity and customization, but and also in low production volumes. For example, I will tell you, I will explain you with a live example. So all of us, we suffered this pandemic, right? Corona. And during the Corona time, a lot of frontline workers, they faced, even the general public also faced the shortage on PPE. So at that time, one of our team from IIT Tirupati, which I was also part of it, we worked on designing, developing the N95 mask. So the process that is being followed here, the time is very short, and we don't want the, we are not going for mass manufacturing in the design phase itself. So it starts with the design. We design it, and then we have also seen the available material and available industry nearby. So the available industry is Amaraja batteries. So they use the TPU material, which is also flexible material that they can use for the battery. So the material is available. We tried, that was in our mind with the designing, and then we designed it, designed the mask, and the mask should fit to the it's not an easy job. No, it fits. It has a lot of functional requirements. It should fit to the profile of the human. Okay, and each human has a different profile, right? And you should have a good breathability. You should have a good 95% purity. Okay, in minimizing the contaminant air. Okay, so we need to give the opening. So it has a lot of features. So we designed it, and then we 3D printed it. Okay, and then the 3D printed mask is being sent for the certification, and then the initial certification was rejected, and then again we redesigned it, and it is certified. And even before certification, we distributed those masks to a few of the hospital people and a few industry people and a few general public, and took their feedback. As per the feedback, again, we modified. This is a complete product development cycle, and we use the additive manufacturing as a tool in designing the product. Okay, and once the product is being made, once we finalize the design, okay, we have given the design to the Amaraja. They went for the mass production. So during the mass production, we use the conventional manufacturing process, that is the injection molding, to manufacture the mask in large number. So now here, if you see, before we go for the final conventional manufacturing, before going for the injection molding, the complete product development cycle, okay, is being executed with the help of the additive manufacturing tool. Okay, so there we try to manufacture the mask in minimum quantity. Okay, it's not in high volume, and it's not customized. Okay, because it should be useful to all the public. Okay, and then it's not that much complex. So here, those are kind of functional prototypes. Those functional prototypes can be manufactured by using the additive manufacturing process. That is, the functional prototypes falls under region 2. So the tooling and fixturing costs are substantially for low volume production. In the sense, if you want to go with the conventional manufacturing for this low volume production, the tooling cost will increase significantly, and the cost of the product will increase significantly. At the same time, the lead times will increase if you go with the conventional manufacturing for product development. And then the examples of the products falling within this region are the functional prototypes, which we use subsequently for the testing and the final before going for the conventional manufacturing for high volume productions. And also the spare parts on demand, they also falls under the second region. Okay, for example, the big aircrafts, okay, jet planes supplied by Russia. So few of the models, they are not in production, and if any of the parts comes for repair, then we don't get those spare parts from Russia. We need to order separately, and they will charge a lot. So what you get is, if we have the CAD model, you can go for the low volume spare parts, and it also tries to minimize your inventory costs. And also the unique pieces to realize the ideas. That is, let us say if you have an idea, there is no need for you to have the complete infrastructure, additive manufacturing infrastructure at your place. So you just have if you have an idea, you can realize the idea by just you make a CAD model, send it to the AM service centers. You have a lot of AM service centers spread across India. Okay, so they have all the required infrastructure to make the product. So make a CAD model, mail it to them, tell the material, they will quote, get the pay the price, and get the product. So So it starts with the idea, and then make the CAD model. You upload it to the service center. You make it 3D printed, get it, and release your product. Your idea can be realized very fast. So, for low volume production of parts, products with minimum part complexity and customization, the use of AM results in lower cost and reduced lead times when compared to conventional manufacturing process. Similarly, the region 3, that means the parts with high complexity, low volume, and low customization. For example, so this is the fighter jet. There's a fuel injector of a aerospace of airplane. Okay, it has multiple components. Okay, if you want to go with the conventional manufacturing process, you need to manufacture those components and you need to assemble it to make this fuel injector. So while doing so, it tries to increase the production cost, it tries to increase the time, and it tries to increase the overall weight. Why? Because you need to fasten it, you need to assemble it by either joining or by fastening. Overall, it increases the weight also. In case of aerospace industry, each gram matters a lot in its fuel efficiency. Okay. So, and these are a few other products. For example, this is a titanium the bracket that we use in the aerospace industry. Okay. So it is been. So this is the conventional way of manufacturing, and this is a topology optimized titanium bracket that we use in the aerospace industry. Okay. So what we do is we can with this additive manufacturing gives us the product complexity. The sense what are the complexity it can handle. Okay. So you please what we do is we need to see what could be the optimum structure with minimum weight, and if we can do the analysis and give it for 3D printing, we can get it. Okay, what is topology optimization? Topology optimization is something like, okay, you have this component and you have some unnecessary material which can increase the weight. Just try to remove that material, again model it, do the structure analysis, see whether it is fitting within the functional requirement. If it is fitting, again remove the material from unnecessary region and then do the structure analysis. In this way, try to optimize your complete weight and the shape. Even though it is complex, don't worry. Optimize the shape and the weight and get it 3D printed. So this is another set of the products which falls under the region 3, that is the complexity advantage. And this is the another fuel injector that we use in the aerospace industry. It has around 19 components. Okay, so those 19 components, we can make the complete injector as a monolithic component. There is no need for the separate components to manufacture separate components. If you want to go with the conventional manufacturing, you need to manufacture the separate components and assemble it to make this injector. So here you can try to reduce the number of components from 19 to 1. The help of the additive manufacturing. Such kind of components can fall under region 3. At that time, this additive manufacturing is being preferable over the conventional manufacturing process. And the region 4, that is the mass complexity. So the same example that we use, this is the engine, aeroplane engine. This is where the injector is being placed. So here 19 components are reduced to one component to manufacture a monolithic component by using additive manufacturing. And here, it's not like that we want it in 1 or 2 numbers. So the aerospace industry require around 40,000 injectors per year. So that means the volume is high, the same time complexity is more. Such kind of components will fall under region 4, that is the mass complexity. So there we can go with the additive manufacturing in case of the conventional manufacturing to reduce the overall production time as well as the cost. And the region 5 and 6, these are the customized, that is the customization and the mass customization. That is the prosthetics. The human prosthetics, these are patient specific. Okay, those are highly customized, and few prosthetics, few implants or prosthetics we don't need in high quantity. So it falls under the region 5, that is highly customized, low complex, and the low volume. So like the prosthetics on the top row, okay, top 2 rows, and the implants in the second row. In case of region 6, that is a mass customization. For example, these are the dental implants.